All right. So yesterday I gave the definition of Shtukas with multiple legs. So the rough plan of these two talks, the first talk will be mostly about geometric constructions that we on the moduli stack of Shtukas. And then after that, I will consider some sheaves on them and cohomological constructions. And the cohomological aspect will be elaborated in Congxue's talk next week. Okay, so let me first just give the most kind of original example of Shtuka, the version used by Drinfeld, just as a more concrete example. This was basically the the version he used to prove GL2, global lengths over a function field. This corresponds to, well, it's he actually defined it for GLN and two legs. So recall from yesterday, we have to choose a dominant co-weight for each leg. For GLN, I choose, this is the first fundamental weight, co-weight. And then it's in some sense, this lambda 2 is the dual of lambda 1. So these two, in terms of representations of the Langlands dual, corresponds to standard representation and its dual. Okay, so then Shtuka with two legs and this tuple of lambda, this pair of co-weights, GLN, classifies pair of points x1, x2 on the curve, and a diagram of vector bundles looks like this. Well, lambda E2 and isomorphic to Frobenius pullback of E0. And the first map, so all these are solid arrows, so they don't have poles, but they have zeros at x1 and x2. Let me call this alpha 1, alpha 2. So the condition is the co-kernel of alpha I is supported, well, is a skyscraper of length 1 supported at xi, okay, for I equals 1 and 2. So E1 has degree 1 less than both E0 and E2. And this is also part of the data, iota. So you can just you can ignore E2 and iota. This would be the same thing. But sometimes it's convenient to separate them. So this is an algebraic stack that maps to x2. So this is taking x1, x2, taking the two legs, realized it as actually relative surface. Sorry, on GL2, its relative dimension is 2. In general, the relative dimension is twice n minus 1. We will talk about what happens in general, how to compute dimensions. Yeah, anyway, so this is what appeared in Drinfeld's original paper. Now, I want to relate Shtukas also to another notion invented by Drinfeld, so Drinfeld modules. Because somehow it's not so easy to write down a concrete Shtuka. Okay, so the Shtuka, by Shtuka we mean a point in this moduli space. So such a diagram. It's not so easy to, well, it's easy to make the first two steps. You pick your favorite bundle, say the trivial bundle, modify it at x1, then modify it at x2. But the non-trivial part is to relate, to give an isomorphism back to the original bundle. And Drinfeld module gives a more concrete way of doing this. And historically, this Drinfeld modules came before Shtukas. So I'll be very brief here, and more details are in the notes. So what is a Drinfeld module? So it can be defined over any base scheme over FQ. So Drinfeld module, we need to break the symmetry a little bit. This is a really not, we need to pick a point. A closed point in X. For simplicity, I'll assume it's a k-rational point. And let A be regular functions on a complement. So that's a Dedekind domain. So Drinfeld modules are really Drinfeld A modules, but acting where? So a Drinfeld A module over S is a pair G and iota, where G is over S is a group scheme, and Zariski locally isomorphic to the additive group. Okay, so the one-dimensional group scheme. And iota is an action of A on this group scheme. That's the data. And condition so let's see. So this is rank, Drinfeld module of rank n. So rank n if it satisfies the following condition. So for any geometric point, little s, let's base change to this field situation. Then this A just acts on A just acts on an additive group. So this is over an algebraically closed field. An additive group over some characteristic P field. So it has some residue field. Let's so maybe S is a residue field of S is some capital K of characteristic P. So this ring can be identified with a twisted Frobenius twisted polynomial in one variable. Okay, so this satisfies A tau. Well, I think tau of A is A to the Q tau. So slightly non-commutative when you pass a constant across tau. So we get this concrete ring, and well, so far I haven't added any condition. It's just pulling back the situation to a point. There, we get a homomorphism from this commutative ring to this slightly non-commutative ring. And the
Is X infinity? You have X.
Can you say again?
Your definition of capital A.
Yes.
As an N.
Oh, yeah. There's a typo here. Thank you. This should be infinity. Yes, thanks.
And Q is the size of small k.
What's the question?
Your Q is the size of small k.
My Q is the size of small k. That's right. Yeah, Q is the FQ, which is the small k. Yes. Okay, so we require an element in A to go to, well, it goes to some polynomial in tau. The condition is on its degree. Degree must be equal to n times the order of A at infinity. Okay. So A is regular away from infinity. It has some pole order. That's the order here. And then multiplied with n. N is called the rank of the Drinfeld module. So that's the definition. And there's this amazing dictionary between Drinfeld modules on the one hand and certain Shtukas on the other hand. So let me explain what kind of Shtukas they correspond to. So I'm going to introduce some kind of Shtukas like this with restrictions. So we have Drinfeld modules of rank n over S. So this is the groupoid of Drinfeld modules, rank n over S. On the other hand, I'm going to introduce a variant of this kind of Shtuka, also decorated by Drinfeld, also rank n. So they will turn out to be equivalent of groupoids. So let's define Shtuka dr. It's very much like this, except first x2 I always take it to be infinity. Okay, so there's only one moving point, and we should think x2 is at infinity. Also, my bundle data is slightly more refined. So instead of having 2 or 3 bundles here, I have a whole chain of bundles that I call so this is a chain of bundles where all the differences are at infinity. Okay, so these, and this is a periodic chain, meaning this bracket 1 is really original bundle where you allow sections to have a simple pole at infinity. Okay, so really the data is E0, this half twist, which is choosing a line I'm explaining the n equals 2 version, sorry. Let's specialize to n equals 2. So this difference is a 2-dimensional space. That's a fiber of E0 at infinity, and you need to supply a line there. And then we will have Frobenius pullback of the whole chain. Their differences are still at infinity. Finally, we have to relate Frobenius pullback with the original bundles. So there will be a map to the next one. Okay, so these diagonal arrows will have all these diagonal arrows have cokernel. That's a skyscraper at x. Okay. So that's the moduli. That's the functor. Okay. So it looks slightly more complicated. It seems you have to choose this extra bundle in the middle. Otherwise, it looks similar. If you just concentrate on part of the diagram, for example, look at this part of the diagram and compare to this. Two bundles and then something slightly smaller. Same here, two bundles and something slightly smaller. Okay. In fact, this looks like there's some extra data here. In fact, there's no choice for it. It's determined by the rest of the data. So this Shtuka dr, I also need to impose that this x is disjoint from infinity. It's a different leg. And I define only for n equals 2 here, but you can imagine for general n, you will have a full flag between E0 and its first twist. But these arrows still go to the right by one step. Yes?
The definition of Drinfeld modules?
Yeah.
Do you take S to be a scheme over A instead, so that you can get the moving?
Okay. So the question is, in a definition of Drinfeld module, should I take S to be a scheme over A? And to get that would correspond to the leg here. The answer is it's actually somewhere hidden in this data. So if you look at how A acts on the Lie algebra of G over S, this is a one-dimensional group scheme. This Lie algebra is some line bundle over S. So this action is given by a ring homomorphism, which on the level of spectrum gives S to what? Gives from S to X with infinity removed. That gives the first leg. Okay. Yeah, so this is how you read off the leg from Drinfeld module. This is classically called the characteristic of the Drinfeld module. So this dr variant of Shtukas is in fact a substack of that one. So if we, the precise statement is there's a closed embedding into the Shtuka on the left board, 1, 2, same lambda, GLN. Then you restrict your first leg to be away from infinity, and the second leg fixed to be infinity. It's not the whole thing, because the dimension here is 3 and dimension here is 2. It's a divisor there. Okay. So this is a very beautiful construction and not obvious at all. And if you're interested, you can read the notes.
Sorry, did you explain it, or?
I did not. Just to give a hint, maybe, how you can build a bridge between the two. not push hard enough. Okay.
Sorry, so this scope kernel we have in the Drinfeld multiple definition, should this be bound like scribe paper of length 1 as well?
Length 1, yes, yes. Thanks. Yeah, so okay, so Drinfeld modules of rank n on the one hand, and Shtuka rank n of a special kind, we can they both embed as full subcategories into something more elementary. That's modules for, on the one hand, has an action of A, on the other hand, has an action of OS, this non-commutative polynomial in one variable. Commuting actions by A and some non-commutative ring, such that this right action is locally free of rank 1. So purely algebraic data now. So this is the endomorphism of the additive group over S. Okay, the Schiffified over S. So this gives the link from Drinfeld modules to this module just by, well, locally, if you trivialize your group scheme to be the additive group, you will get such a structure. M will be identified with this, and it carries an action of A. This is more interesting. This step, this M, how you get M is you take, starting from a Shtuka data, you take global sections of, just of E0 on the punctured curve. So that's some OS module. And you need to use the Shtuka structure to equip it with some Frobenius twisted linear endomorphism. Okay, it's obviously an A module, but yeah. So I think that is a brief explanation. Okay, so let me also just to get some more concrete ideas about what Shtukas are. Let's try to, well, I'll talk about iso-Shtukas. So this is not geometry, it's just a coarse description, of points, Shtuka, whatever, k-bar points. It's not even a precise description. That's the, but only up to isogeny. Okay. So we want to describe k-bar points, Shtukas over k-bar by some linear algebraic data. If we look at a Shtuka, right, over k-bar, this means I have G bundles or vector bundles that both live over not X, but X space change to k-bar. And then E is identified with the Frobenius pullback Frobenius along the k-bar direction through some map that's an isomorphism away from finitely many points. So this data we can restrict to the generic fiber, to a generic point of xk bar, to get something that deserves to be called iso-Shtuka. So what do we get when we restrict to the generic fiber? Well, it's just a vector space over the function field of this curve. Function field now becomes the original f base change to k bar. Okay, so this is analogous to the isocrystal story. We use f brev to denote this larger field. So we get a vector space V. This is a f brev vector space. Suppose we're talking about GLN. Okay, so these are rank n bundles. Then we get a n-dimensional f brev vector space and a Frobenius twisted map, linear map. So this generic fiber is also V, but then this map is not f brev linear. It's only so f linear, and in the k bar factor, it's Frobenius semi-linear. Okay, so we get such data. We forget about the legs for now. At the generic points, these are just isomorphic, but in a twisted way. So this is the category. We define this to be the category of iso-Shtukas for the global field F. Okay, so they are not vector spaces over F. They are vector spaces over F base change to k bar. So it can be of any dimension, and there is a Frobenius linear isomorphism, linear automorphism on V. So that's analogous to isocrystals. Indeed, there is a passage to isocrystals. Suppose X is, for simplicity, k-rational point of X. Then we have the category of isocrystals over this local field. So again, these are vector spaces over this fx brev, and then together with the Frobenius linear automorphism. So clearly we can pass from iso-Shtukas to isocrystals over fx just by tensoring. Localize it. Okay, so and this phi, okay, I should call that map phi, Frobenius linear map. Of course, just extends by the Frobenius just extended to be Frobenius linear map. If X is not a rational point, here you need to raise this to a power such that it becomes an isocrystal. Depending on how large the residue field is, you may need to pass to a power. But there's such a functor for every closed point on the curve. Okay, so for isocrystals, we have a classification. It's already appeared in other talks, Dieudonné-Manin classification, which says isocrystals, simple objects, simples. Well, first of all, this isocrystals form a semi-simple category, and the simple objects are classified by slopes. which can be an arbitrary rational number. And there's a description of its endomorphism ring. So let me just, so there's a, if, yeah, so if lambda is a rational number, we have some simple isocrystal of slope lambda, then the dimension of fm lambda over this brev is the denominator of lambda in lowest term, and then endomorphism of m lambda as an isocrystal. This is central division algebra over fx with invariant, well, minus lambda. That's the convention. But you see essentially you see all different kinds of central division algebras by taking endomorphisms, well, the modulo z, by taking endomorphism of isocrystals. So there's a completely parallel story for isocrystals. For iso Shtukas, yes. So this is due to Drinfeld's description, parallel to Dieudonné-Manin of iso Shtukas over F. So first, this category is semi-simple. Second, simple objects. Okay, so that's a little bit more complicated to state. But the answer is very nice. You take separable closure of F, take its multiplicative group, and then you tensor up to Q. So just view it as an abelian group tensored with Q, and then you divide by the Galois action. So this is a well, at first it looks mysterious. How do you get a number algebraic over F out of a iso Shtuka? Yeah, so maybe if people are interested, I can explain during Q&A. And now you can see the relation with the isocrystals. So if you localize, so if this is a simple object, v comma phi, then localize it, you get an isocrystal. And this, well, in general, will not be simple, but yeah, okay. So it's a little bit complicated to state. So suppose I take a simple object, then there is some finite separable extension over F, such that the corresponding element is realized there. And I pick the smallest one. So this is some invariant A that lies in LA. Okay, so I have some representative of Galois orbit, and I pick the smallest separable extension where A lives. So this field is the analog of is a field of complex multiplication on geometric objects. So you can think of this V phi has Cm by L A. So it has more symmetry than what's obvious from the definition. The A is a function on. So A is in the extension, in some extension of the function field of X.
What is the L sub A?
LA is determined by A up to Galois, is the smallest field where A is realized. Okay, then if we calculate endomorphism ring of this simple object, we get some answer, similar answer. This is a central division algebra, not over F, but over this LA. And its local invariance at, now I can talk about local invariance at a place of LA. So this is more refined than places over X. But the formula is just order to assign. There's an order of A. So A is, A you can think of it as a rational divisor on the curve whose function field is LA. Right, so it has a vanishing order or pole order at every place of LA. That's a rational number. And then you multiply with the residue field extension, the degree of the residue field extension. Again, that's some rational number. That's the local invariant of this central division algebra. So locally, it may further split up, but it's still a central simple algebra. And if you restrict, so now it makes sense to restrict to a place not just in F, but also in this field of Cm. When you restrict, you get an isocrystal over Fy. Well, maybe this, not Fy, Lay, and whose now it's an isoclinic with a slope. This number is exactly this number. Yes, it's slightly more complicated because of this field LA can be not F, but other than that, it's just the global analog of isocrystals.
Isoclinic means direct sum of.
Yeah, so isoclinic means a direct sum of the same simple object in isocrystals. Yes.
Can you explain a little bit some motivation behind all of this? Like, why did you present Drinfeld moduli, for example? You said something about Cm field here, and we don't see any complex multiplication. Are you planning to say anything?
So I can give some just a very brief answer now, but maybe explain more in Q&A. Yeah, so this kind of description of k-bar points is you will need it if you want to count rational points on the moduli of Shtukas. And why do you need to? And why do you want to count rational points? Well, you want to do something that people usually do for Shimura varieties is to compute Lefschetz trace of operators on the moduli of Shimura varieties or moduli of Shtukas. It requires describing rational points on special fibers. And the first step in listing all the points is to classify them according to isogeny. So say you're classifying abelian varieties over Fp bar with some extra structures, you first want to classify according to isogeny class. And this Shtuka is the analog of that step. You break up into isogeny classes, and then you, for each isogeny class, you have some kind of model object, model Shtuka, and you compare, you look at what are the freedoms of modifying that model object at local places to get arbitrary Shtuka. So in short, this procedure is needed to understand point counts on modular Shtukas, and eventually applied to comparison with Arthur Selbert trace formula, for example.
And what about the Drinfeld modulus? Why were they introduced?
In this talk, why? So I wanted to, for Drinfeld module, the reason I introduced it is because, well, it was the origin of Shtukas. And also, if you really want to write down a Shtuka, you probably, it's easier to write down a Drinfeld module and then turn it into a Shtuka. That's, I personally never really wrote down a Shtuka. So okay. Yeah, there are probably other explicit ways of writing it down. Okay. Yeah, so I'll just say it verbally. This category has an analog for number fields as well, constructed by Kottwitz. It would be very interesting to know what does it classify, what kind of either algebraic or geometric objects it classifies. But that's still quite a mystery. Okay, so let's now go to some more geometric properties.
Is it like Hecke category of Shtukas over F? And the germ is the Koppel's germ?
Yes, yeah, that's the precise relationship. That's a Tanakian category over F, but not neutral over F. Yeah, it's classified by the Kottwitz germ. Okay, so now let's move on to some algebraic geometry, geometric properties of moduli of Shtukas. So I'm mostly following Warshawski, who introduced these general notions of Shtukas for arbitrary reductive groups and arbitrary legs in around 2000, 2004. And that's what Vincent Laforgue used to prove his big result. Okay, so the basic fact is, if we consider this iterated version of R legs and arbitrary modification type, so less than or equal to lambda. So this is an algebraic stack locally of finite type over, over x to the r, over the legs, of course also over k, with relative dimension. Well, there's two cases. Okay, so either it's empty. We've seen examples, so this means it's empty. If these co-characters are not chosen in a balanced way. More precisely, it means if you sum up all these lambda i's, it does not lie in the co-root lattice. Then you don't have Shtukas at all. And if the sum lies in the co-root lattice, the dimension is, so relative dimension relative to the legs is a sum of 2 rho paired with lambda I. So this is exactly the dimension of, so this is under the condition this inside the co-root lattice. So recall we have Gur lambda. This is an orbit, G of O orbit inside affine Grassmannian. This has dimension 2 rho paired with the lambda. Here, 2 rho, well, this has been, it's shown up many, many times. The sum of positive roots. Lambda is dominant. Okay, so yeah, so there's some general property, algebraic representability by algebraic stack, locally finite type. And then this dimension formula also suggests a close relationship between Shtuka and Grassmannian, maybe just the product of these Grassmannian. At least they have the same dimension. Okay, sorry, so maybe the version, so the fiber-wise looks like this. Dimension are the same. But in fact, one can say things more precisely. So the question was how does this dominance condition on lambda contradict that the sum of lambda I being in the co-root lattice? It doesn't. I mean, you can have negative entries in the dominant co-weight. The first example I gave, these are the lambdas. It's just the ordering, right? Decreasing order, but you can have negative entries for GLN. They can sum up to 0. Well, you only need the sum, summing all the numbers inside, that sum is 0. Okay, so more precise version also proved by Warshawski. Is locally for the état topology, we indeed have an isomorphism. Well, again, so this is in the sense of local model. So namely, there's some stack that maps to both, and both maps are état. And so if you're standing at a point here, you can find some état cover that also has an étale map to the other side. Okay. So this is saying not just they have the same dimension, but they have the same singularities. Okay. So in particular, if you take all lambda I to be minuscule, then mentioned yesterday in Q&A, GER lambda I is equal to GER lambda less than equal to, well, it's its own closure, and it's isomorphic to a partial flag variety of G. In particular, smooth. And in this case, we conclude that the Shtuka moduli space is also smooth. Smooth over x to the r of the dimension specified above. Okay, so in particular, in the Drinfeld example, these two are both minuscule, and it implies Drinfeld Shtuka moduli space is smooth. Okay, so let me see. So just thinking, what should I talk? Okay, so I needed to introduce a slightly more complicated version of Shtuka. Just it's more canonical. So far, we have worked with the iterated version of Shtuka, which means a bundle with ordered several steps of modification and arriving at its Frobenius pullback. There's also a non-iterated version, which is actually harder to define. At least if you want a bounded version, it's harder to define. So we really want to, conceptually it's better to start to index these legs not by 1 through r, because that implicitly contains an ordering. We don't want to order the legs, just take a finite set, and we want to define first, without any bound, what is Shtuka Gi? Well, this is easy to define. So you just have legs indexed by I, and you have a bundle, G bundle, and its Frobenius pullback, an isomorphism away from all these legs. So alpha is iso when restricted to the complement of all the legs. So this, when you plug in a test scheme, these mean graphs. Okay, so you don't order the legs, but you also don't do the modification step by step. Okay, when the legs coincide, it's not. It's impossible to. There isn't a unique way of connecting E with tau E in a well-defined step by step. Okay, if you have two different legs, you can always modify it at one leg in the first step, modify it at another leg. But if legs coincide, there are multiple ways of decomposing it into iterated Shtuka. So the bounded version is more complicated. Actually, what it is not so important. But let's just give an ad hoc definition. So I want to use the same data. Suppose I have a tuple of dominant co-8s. Now I want to define Shtuka I less than or equal to lambda. So what we can do is we just choose an ordering. And now we can, the iterated version is defined. It maps to the non-iterated version just by forgetting the middle steps and just take the image. Okay, so this definition. It's not obvious why why this definition is independent of how you order I. It turns out to be, yes, it is independent of ordering. But anyway, so the role played by this space is not quite that we want to study, like, say, it's really want to study its algebraic geometric properties, but rather I just want some space to host a sheaf, which we will see later. So this space is enough to host the sheaf. So that's, yeah. So maybe beginning of the next lecture, I'll just give one example of what this looks like, and then we'll move on.
Thank you. Any question?
Does the analog of Bartowski's theorem also hold for non-iterated Shtukas?
Question is, does the analog of Warshawski's theorem also hold for non-iterated Shtukas? The answer is yes. There is a version where you replace the Grassmannian also by the non-iterated version of Baylin's and Drinfeld Grassmannian.
Other question? Yes?
This map you have here is an isomorphism away from the diagonals of X.
The question is whether this map is an isomorphism away from the diagonals of x to the r. The answer is yes. So, well, so if I didn't put a bound here, this map is iterated mapping to non-iterated, both map to x to the r. And if you restrict to x to the r disjoint, so meaning all points are pairwise distinct, then this is an isomorphism.
Other question? No? Okay, so we will resume in 20 minutes.